I'm away. I'm traveling, so I'm in another town in a hotel room. So
okay. That's
I was a little worried if the Wi-Fi would be a problem, but I'm glad that it doesn't seem to be so.
Okay, very good, sir. Very good. Professor Tom is also attending the session. He's also already there.
Yeah. Good evening, and Jay, Tom, Matthew.
Tom, how are you?
Yeah, fine. Yeah. Very excited to hear you.
Well, good to see you.
Professor Jayakrishnan, shall we start?
Yes, I can. Let me make sure that there is no problem in sharing the screen.
Okay.
How do I share my screen?
The camera is here.
I have not used the WebEx much at all, so I'm a little doubtful how to share.
Take your own text.
Yeah, no, got it. I got it. I will. Okay. All right, so this should work. Can everybody see that?
It's coming. Yeah. It is there now.
Okay.
So,
good morning.
Shall I start?
one minute.
Okay.
Good morning, professors, researchers, scientists, experts, and students. It's my pleasure to welcome you all to the technical talk series organized by NATPAC. As you all know, that NATPAC, an institution under Kerala State Council for Science, Technology and Environment, is a premier R&D institution in the country which works on multimodal system of transportation. Through this technical talk series, we aim to provide a platform for experts in this field to share their knowledge and expertise with us. Today, the third talk series in the series will be delivered by Professor R. Jayakrishnan on the topic Traffic Signal Control of the Future, Should We Do It at Intersections? Before we begin, I would like to extend a warm welcome to Director NATPAC, Dr. Samson Matthew, who is going to deliver the welcome address.
Thank you. Good morning, everyone, and good evening to Professor Jayakrishnan. It's an honor to welcome all of you to NATPAC's TransTech talk series. Every month, we conduct this program with a talk from an expert from the transportation field. This is our third lecture in this series. First technical talk was delivered by Dr. Srinivasa Kulgutra on the topic advancing crash frequency predictions using modeling using GIS, which was organized by the Traffic Engineering and Safety Division. The second talk was by Dr. Rajib Malik on the topic of on the challenges and solutions in cold asphalt pavement recycling, which was organized by Highway and Bridges Division. As introductory remarks mentioned, NATPAC is working under the Kerala State Council for Science, Technology and Environment. It was established in the year 1976, and in 1982, it was constituted as an R&D center under the Department of Science and Technology, Government of Kerala. We have 5 divisions: Transportation Planning and Engineering Division, Traffic Engineering and Safety Division, Highways and Bridges Division, Water Transport Divisions and GAS, and 5th division is Information License and Training Division. At present, we have 22 scientists, 8 technical officers, and 7 technical assistants are working under these 5 scientific divisions. Our research activities are guided and monitored by Research Council under the chairmanship of Professor Tommy Matthew, who is also attending this today's talk. Welcome, Professor Tom, to this session.
Thank you.
Other RC members are Professor Lalita from IIT Madras, Professor KS Reddy from IIT Kharagpur, Professor Remiela Ranjanelli from NIT Calicut, Dr. Velmurugan from CSIR CRRI, and Professor Ashalada from College of Engineering, Trivandrum. This month, the Transportation Planning and Engineering Division of NATPAC organized this talk on traffic signal control of the future. Should we do it at intersections? To introduce our TPD division, a very dynamic division, it is headed by Mr. Yash Shaheen, the principal scientist, and the scientists include Mrs. Shalini Pian, Mr. Anish Kini, Mr. Arun, Dr. Praveen P.S., and Dr. Anila Sirin. We are very excited for today's session on traffic signal control, which is indeed an interesting topic going to be handled by Professor R. Jayakrishnan, the Director of the Transportation Science Program at the Institute of Transportation Studies at the University of California. In fact, I'm very happy to welcome you to this session because when I joined this institute as director on 2020, January 1st, in fact, Jayakrishnan was also with me that day. And I completed almost 3 years, 4 months with your support and all. Welcome you, Professor Jayakrishnan, to this talk. I'm very happy. Thank you for accepting our invitation and at very short notice, in fact, you agreed for the talk. Welcome you to NATPAC again, and it's so happy that he's from Kerala and he's having a special to NATPAC. Thank you.
Thank you so much. It's very nice to hear from you. We had all the plans for an MOU with the University of California at Irvine and NATPAC, but COVID came in the way right after I visited last time. So we will take that up again too. So anyway,
we'll take it forward, sir. Now we have time now. We will do that. And it is an honor to welcome all the participants to today's lecture series. Almost 64 participants are attending through online across India as well as from outside the other countries. So welcome all of you to today's lecture series. We have participants online from prestigious institutions like IITs, NITs, and other government colleges. Welcome all of you to this session. I request all of you to you can ask questions. Probably you can message that one through the chat box, and at the end of the session, probably we'll give some interactive session so that your doubts can be cleared. Thank you once again for joining us today. You are here, and we are eager to get started. Thank you. Over to Jayakrishnan.
Thank you so much.
I would like to invite Sri Shaheen S. and head of TPD NATPAC to introduce the speaker for today's session.
Good morning to all. This opportunity, welcome Professor Jayakrishnan sir to the third talk series NATPAC. I have given the task of introducing the speaker. Professor R. Jayakrishnan is from Chengalur, Kerala, has been working as a professor of civil and environmental engineering at the University of California at Irvine since 1991 after receiving his BTech from the Indian Institute of Technology, Madras in 1985 and his doctorate from the University of Texas at Austin. He is the director of Transportation Science Program at the Institute of Transportation Studies, University of California, Irvine. His research interests are in a variety of topics such as traffic flow theory and simulation, transportation systems and public transit designs. He has been in the editorial committees of journals such as ASC Journal of Transportation Engineering and the Transportation Research Series, and has served in several professional committees and academic panels of the Federal Highways Administration, National Science Foundation, and the Transportation Commission of Seoul, South Korea. 26 PhD students have graduated under his advice, with half of them proceeding to faculty positions and around the world. He has about 150 referred publications to his credit. Today, the talk is about the traffic signal control of the future should be dual-lit intersection. It will explain the intuitive basics of traffic control that are traditionally taken for granted, and will discuss the possibilities of a new paradigm in traffic control that is link-based for this purpose. Let us welcome our speaker, Professor Jayakrishnan sir, for today's talk. Welcome, sir. Over to you, sir.
Thank you, Shaheen. So hope everybody can hear and see the slides. And I'm also glad to introduce my co-author, my student, PhD student, Pengyan Sun, who has also joined with me. Some of the work that I'll be presenting today is done by Pengyan. And much of this came out of our discussion. So I will get started with that. Okay, outline what I wanted to do in this talk was to keep it technical but qualitatively technical. I'm not planning to give too much of quantitative items, formulas, and all of that. In fact, I'll throw some slides at the end, which are slides from Pengyan, because that's hard work from him. But the ideas behind this is what I am hoping to present. So basically, I wanted to take a look at how we are doing traffic signal control, how we have been doing it for the past century, and should we actually even change our thinking when it comes to the future, especially knowing that there will be better technology available. In fact, better technology is already available. We have autonomous vehicles as a possibility, even though nobody expects that at this point. Nobody expects autonomous vehicles will be prevalent on our streets for at least another couple of decades, if not more. But signal control can be changed with existing technology and some of the technology that is becoming available. Then additional thoughts came to mind. Most of this started when Pengyan was starting his PhD work, and he was looking at traffic smoothing, basically bringing vehicles to intersections, green driving, basically, of bringing vehicles to intersections. And then as he was putting a proposal together, we were having a phone conversation. It was literally a phone conversation during COVID times, basically, I guess. And then this idea just struck that, hey, why do we even think of having signals anymore at the intersections? I mean, where should we place these signals? And that's where the research went. Then that kind of forced me to look back at how traffic signal control has evolved and how our thinking has been. So if we go back to the history of traffic control, of course, it was 1868 when they first tried traffic signals in London, of course, and it was a semaphore system. Like I'm not sure if all of you remember the semaphore arms that we have on railway tracks. They used to have that. I mean, you can actually see the picture where they had these arms that were set up as traffic signals. First electric signal, of course, it was after electric bulb and everything got invented and all that. And then first electric traffic signal was developed by Lester Wire at Salt Lake City, Utah. And then by 1935, USA had the first manual on uniform traffic control devices. Interestingly, that's a book that title has not changed even now. It is still MUTCD. that the US has. Of course, it's been updated so many times, and you can see some of the earliest traffic control. There was even a little bird cage kind of thing, where a policeman would actually sit inside that inside that little bird cage. And this was actually because it was developed by Lester Wire. It used to be called a wire on a bird, or a bird on a wire, or something like that. I don't remember. And this is 1868 when London first started traffic control. It had some lights, gas lights, etc. They had some big fires and problems of that kind. But you can see that by the signal caution, all persons in charge of vehicles and horses are warned to pass the crossing with care. So these things were, we've been doing this for quite a long time, 150 plus years. So what have we been doing? Basically, we have red signals and green signals at intersections, as all of you know. Many of you would have designed, and I'm sure almost all of you would have studied it. So I'll just remind you on your class notes. What happens at a traffic signal? We do not allow traffic streams with crossing conflicts to move. I mean, that has been our thinking always. We won't let crossing movements to happen at an intersection. Now, you might know, and you may have seen computer scientists a few years ago doing autonomous vehicle simulation, showing that this vehicle can just go through. But they were basically using schemes, sort of like random path finding, etc., that robots would do. But those were not like an optimized scheme where engineers could actually say that, okay, this is how we will design it. We will still need signals, at least in the near future, when a lot of vehicles will still be driven by human beings, at least for the next 20-30 years. So the best we can probably hope for is that there could be technology that could assist us, more like level 3 sort of automation, but fully automated vehicles may not be what would happen in the near future, at least. So anyway, back to traffic control. 2 streams are allowed at a time, 2 through movements, or 1 through movement and 1 left turn. In India, it will be 1 right turn, or 2 right turns that can happen in a 8-phase ring diagram. So some streams of merging flows, just right turns in the US or left turns in India, they are allowed. Left turns are allowed unless otherwise specified for congestion reasons. Again, not for safety reasons. And that is the well-known RTOR in right-hand driving countries, and LTOR, or left turn on red prohibited in India. I don't think it is used a whole lot in India, but it's there. How safe are merging or car following movements in comparison to crossing movement? This is a question that really came to mind. We have always lived with the thinking that we can merge. We don't run into accidents in merging. We have expressways everywhere now, or freeways in the US. Vehicles are coming at 60 miles per hour, 100 or 120 kilometers per hour speed. And there's an entry ramp, and people easily merge. And that merging is happening probably into gaps which are no more than 3 or 4 car lengths. We can do that. Seemed like we never bothered to be scared about that. Why are we so scared about crossing movement? That is sort of where my thinking went. So we will revisit this question. And one other thing to keep in mind, that we have all of us who have learned driving, we are constantly keeping safety when we are driving in car following. We do this constantly, every split second. It's completely in our mind. We are not even thinking about it, and we are doing it. And we know that our foot is doing so many things to make sure that we won't hit another car that is in front. Why are we so worried if a car is crossing us? This may not be a problem in India. In fact, we see on our national highways that we do know how to cross into traffic. It's not an impossibility. impossible maneuver. I think human beings can do this, and that's where the thinking went. Let's just step back. What happens at a traffic control? So it's class notes that all of you would have seen. So I simply borrowed, this was from a talk that I gave to the students. So I borrowed the notes from my colleague, Wenlong Jin, Professor Wenlong Jin, who I consider the foremost expert in traffic flow theory in the world itself. That's just what I have always thought about him. These are just his lecture notes. I mean, I used to teach this class, and many of you teach traffic engineering, and many of you have taken the courses, so you would all know this. If there is a queue that forms whenever there is a red light. There's a green phase at the light. There's a red phase, and if you just think about a straight deterministic queue, there's an arrival curve, and then there's a departure curve. Departure curve gets stopped during the red time, so it becomes flat, and then you get the saturation flow. Then they leave. Now what happens is the area in between these two curves is the total queue delay that is caused at an intersection. I mean, this is well known, right? So you would have all seen these equations, and I'm sure you know the delay formula that is given there, the well-known Webster's delay equation. And the problem is that when we have all learned traffic engineering, we look at these formulas and we don't really think too much about it. It's like, oh, there was that complicated formula that Webster came up with. There's really nothing too complicated about it. The first term is pretty much what applies for most purposes. The second term is showing the extra delay due to randomness. And of course, Webster's used it. Webster's thought it was going to be Poisson arrivals, and so of course the traffic is not following Poisson. It's much more correlated movements than Poisson. So you need an adjustment factor. So all of these things are added, but the primary aspect of delay is basically that first term, and that first term is simply coming from the blue area. That's it. So many of you would know this. So just keep that in mind. If you continue with that thought, what is the effect of the cycle length? If you look at that formula, you'll actually see that the cycle length will get affected by the. Cycle length will affect the delay. Again, it may not be that obvious from the formula, but it is when you actually look at the cycle length and the total queue time. You can see that if you had a cycle length which is twice as long, which is the left figure, as compared to the same cycle being split into two smaller cycles. Now you can actually see that instead of getting one triangle, you have two smaller triangles. But the smaller triangles, 4 of them add up to make the one in the left, right? So the area basically ends up becoming half, and that's what really happens. The total queue delay is the area, okay? So cut the cycle into half, and the total delay and the average delay also becomes half. Now this is, you would think that this is elementary, that yeah, we all know this, or do we know it? If you look at traffic signal settings around the world, I would apologize for the country where I am in, mostly taught from the US to all the countries around the world, particularly Asia. Almost everybody seemed to have learned it from US and UK. And somehow we have never been told that long signal cycles is a bad thing. And we always give the reason that, oh, it is all for pedestrians. I mean, that's almost like a convenient excuse. But for pedestrians, yeah, we have to give that. No, pedestrians can wait a bit too. You can do it a few cycles at a time. Okay, it's not like pedestrians need. The reason why I say that is because if you are keeping these long cycles and you're basically causing much longer queues than you really need to. So you need to think about it. This has not been much appreciated. India is not too bad, by the way, in this. When I drive through Kerala, I actually don't see single cycles which are that terrible. But you know, you go to other places in Asia, try Bangkok or try Seoul. You know, these are all places where you'll see like 4-minute type of cycles. Just what are you doing is what you would think. In fact, all of those queues are caused by those cycle lengths, nothing else, which is you know, when you think about it, we should actually appreciate this is a little bit more. We need to try to cut the length of our cycles. I mean, that's one of the basic points that I wanted to make, and that actually you know, continued the thought. And then, so what happens when the cycle length goes up? We have this average delay curve, which you may have seen again. And if you look at a lot of the textbook discussions, lecture notes, and everything from all the way from the 60s and 70s, they have always kind of told us, okay, you might have that minimum delay point, like what the Webster's equation might give. But don't worry about it. If you, for pedestrian reasons, if you need to make it 2 times, yeah, go ahead. It's sort of flat out there. No, it is not flat. Again, we have to actually realize this. This curve is basically asymptotic with respect to a line from the origin on the right side. In other words, it is showing the same behavior that I was earlier showing. If you give twice the cycle length, you will get twice the delay too, average delay. So we need to keep that in mind. Now, all of you, or most of you, would know that the left side comes down from infinity, and that's because there is lost time. I mean, if in every cycle you lose 10 seconds or 20, you know, 15 seconds or whatever at a signal, which is just lost time, startup lost time, yellow times, right? So which means if the cycle length becomes too small, delay will just go to infinity. So we don't go anywhere near on the left side of this anyway. We work on the right side. The problem is we work too far on the right side. And that's something that all of us should think. I mean, in this talk, I wanted to just throw these ideas and thoughts back at you. Some of you may have thought about this. If not, you know, just spend some time when you want to think about the traffic control that we do. So anyway, so we have lost time. The lost time is fixed, as I was saying, the 3 to 8 seconds, depending on the phases that you have. And so about 15 or to 30, anywhere between 15 to 30 seconds could be lost in each cycle. That's a problem with these with these cycles, which means the only option is sort of keep it long, and then pedestrians will often give you even more trouble. And those of you who would have worked as traffic engineers, and I haven't, right? But those of you who have worked as traffic engineers would actually know this pedestrian problem at many intersections, when, especially in Kerala, when you have a primary street. Kerala is not a grid structure. I mean, we almost any of the major thoroughfares that we have through all those streets, the major highway typically has minor crossings. And if you ever have a signal at a minor crossing, we have to set the red time on the major direction because of the big width that you have for the major direction. So then what that ends up doing is that, okay, if you have to give 50 seconds or not 50, 90 seconds time, red time to the predominant direction, you will then have to give 200 seconds for the cross direction, which is less traffic, because the green times need to be in the ratio of traffic flows. So these things are just killing us. Is the point that I wanted to make. In the end, we are ending up having these cycle lengths which are really, really long, and that's a problem. Keep that in mind. I've said it probably 5 times already. Link-based control. How did we think of this link-based control in a perfect world? Let's just go back to the queue diagram that I was showing, which was a perfect world, right? Because the departure curve is like a vehicle comes along a straight line, immediately goes flat, and then immediately goes to saturation flow rate. And that's a perfect world. No vehicle stoppage and no lost time. So in that case, what is the best cycle length? I have asked this question in my traffic engineering class to students, and only one student has ever answered that question, which almost surprised me. And he happened to be a Malayali, right, from Kerala. In fact, Panyan will know, Navjot Sharma from Kollam. He's the only one among my students who have ever answered this question, which has a simple answer: make it as short as possible. Which is okay. Then what is it? About 1.8 seconds, 2 seconds saturation flow rate. Because keeping it anything less than that doesn't make sense, because cars following each other will typically be no less than 1.8 seconds, more like 2 plus seconds apart from each other. I mean, that's our saturation headways that we have. So that's the minimum green time that we should give. So if we are now gonna give this, then it'll be, if you give a green and then a red for the cross direction, then you need 3 seconds total. So with 1.8 in each direction, right? So still it's only 3.6 seconds per movement if we assume 50% green split. I'm just talking about a very simple intersection of two one-way streets. One lane, one-way streets, okay? The simplest case that we can all think of. One lane, one-way streets in cross directions. If we actually give a 50% green split, then we know that it'll be 3.6 seconds and 1.8 seconds for each of those. Still, we won't get any more than 100 vehicles per lane per direction. That's actually pretty good, but it is not much more than what we would get, in terms of critical volumes. The total sum of critical volumes at an intersection, which is basically the critical lane volumes in multiple directions, they will add up to something no more than 1900 or so, right? So we know the total critical volume will only go to around less than 2000. But once you adjust it with the capacity manual, now India has a capacity manual. Tom and others have worked a lot on those, on the capacity manual. So if you look at the capacity manual, you'll actually find that the sum of critical volumes typically come down to probably 1300, 1400, no more than 1600. Okay. So problem is that this worry about crossing movements and is just killing us. Is the point. So if we were to think about not stopping at the intersections, like the autonomous vehicle people have been saying. Did I freeze at your end?
No, Professor.
Can you hear? Because the video froze. Okay, the video froze at my end, so I was wondering why it was. Okay, so if you talk to the autonomous vehicle people, I mean the modelers of autonomous vehicle flows from even 7, 8, 10 years ago, they were simulating autonomous vehicles just kind of randomly going through gaps through an intersection. I'm getting a message here that WebEx meeting problem report, WebEx meetings is not responding. Could Shahim, maybe you could send me a WhatsApp if I totally freeze?
No, Professor, you can continue.
Yeah, I will continue. But if something goes wrong, let me know.
Sure.
Okay, all right. Okay, so so the solution for this was, can we actually send one vehicle in both of these directions every 1.8 seconds, and they just go through each other? Do we have enough gaps to do this? If we actually regulate the arrival of the vehicles, we can actually regulate very easily by keeping a signal upstream on the approaches and release a vehicle every 1.8 seconds. They need to be timed. if there is a gap of 1.8 seconds between two vehicles, then the release of the cross direction vehicle needs to happen somewhere in the middle, so the car can safely go through it. Plus, a collision avoidance technology would be really useful. But that exists. Many of the new cars that are coming out, all of the Teslas and autonomous cruise control vehicles, and many of the cars coming out of Europe, cars being manufactured in, collision avoidance technology is no longer a problem technology. It's very much there.
There is any problem there, sir? Okay. So we will once more we will initiate this. Okay. Okay. Some technical problem will join. All the participants, there is some technical glitch. Sir will be joining soon.
Okay.
Sir?
Hopefully, I'm back.
Yeah, okay, sir. You're back.
Okay. So let me just go through the explanation that I was saying. So anyway, that's the idea about the link-based control, where we release vehicles. Much more study is needed on this, of course. As the vehicles are released, there are some interesting aspects to this. When the vehicles are released from these mid-block gates, which I mean, it's not mid-block, they are probably about 100 meters maximum, somewhere between 30 and 60 meter away would do upstream of the intersection. So we won't have any signals at the intersection, but we will just simply have a signal which is a flashing green that flashes every 2 seconds or 3 seconds or whenever in a timed manner. Okay. But then what is going to happen is, once a vehicle that goes through a gap and gets to the next block beyond the intersection, it may be getting to the flashing green again at at the right time, because this actually forces gaps between vehicles that are in a stream. And those gaps will actually continue from intersection to intersection to intersection. So you will be reaching each of these flashing greens when you may not even have to stop. And that is that's the beauty of it. And we have actually simulated it. But the real question is, will there be gaps to go through? This is really scary. Everybody will think this is a really scary idea. Simple example, vehicle release every 1.8 seconds. Let's say the speed that we are looking at is about 40 kilometers, which is actually pretty high. The space gap between two successive vehicles is about 40 meters, about 8 car lengths or so. We can easily go through a gap between those cars. Again, remember that we won't have the car bunching phenomena anymore, because we are releasing vehicles from each of these gates, with the green signal. These will be just like the signals that are used at expressway entries. If you have ramp control, India really does not use much of ramp control. But around the world, there is ramp control that goes on, where there is a flashing green that lets a vehicle go into the freeway or expressway at every 3 seconds or whatever. So this is very similar to that. It actually causes gaps between vehicles. And once there is a gap, you're talking about 8 car lengths of gap. Another car can easily go through that. And this is the issue. Why don't we allow conflicting movements if there are that kind of gaps? Now we can release vehicles every 1.8 seconds. Now, then there is no need for any cycle. Ideal case. Ideal case is one vehicle goes through every 0.9 second through the intersection. East-west goes every 1.8 seconds, and north-south goes every 0.9 seconds. You can actually get throughput close to, in fact, 2000 is wrong. It's actually 4000 that you'll get. The current maximum is 1500. I simply made a mistake in the number. It's 4000 vehicles throughput that you can actually get through an intersection with this, which is almost unbelievable that you can actually get this. So you have to simulate and see if this is possible. If we stop only worrying about crossing conflict, we can do this. That is the point. I know this is too ideal. What about bikes? Okay, that question comes up. Then trucks, autos, pedestrians, cows, chickens, Kerala drivers coming out of beverage shops. All right. Yes, those things are to be studied in field tests. So this is early. This work, and in fact, it's the first presentation that I'm giving you, that I'm making on this idea to anybody other than students at ITS. In the first paper that I wrote on this, that Penyu and I have written, it's a short paper, and that has been just sent to TRG at the end of this year. But more elaborate journal papers are coming soon. But back to the topic. But will there be gaps for these vehicles to go through? So we can easily go if we time things right. That was the point. So critical volume, we can get a lot more if we stop worrying. But now the question is, how serious is the accident probability if vehicles are going through this? Maybe I should show you a little video from Panyu, and that I wanted to show you. This is an example. I may have to. I don't think you can see a video yet, right?
Not yet, sir.
Yeah, I think I have to stop sharing and
Yeah, correct.
and start sharing again, right? Yes. And I have to select that to share. Okay. Can you see the video?
Yes, sir.
Okay. Can you see the cars going through? Did all of you see the video?
Yes, yes.
Okay, so let me just go back just to make sure you can actually see the distances between the cars. This is a normal situation that Peng Yuan actually simulated using our own simulation model. He's a Tesla and Toyota Corollas, I think, or something. Toyotas and Teslas that are crossing each other. These are two-lane traffic. It gets a bit more complicated in the two-lane case. You need to make sure that multiple lanes traffic actually comes somewhat in a timed manner for them to go through. There is a very interesting optimization problem that we have actually solved on this. But I'm not planning to get into the details of that optimization. There is some more. Now you can see that there's a lot more vehicles that are going through. This will be really scary for people who are driving, but if we know that there is technology assistance also there for collision avoidance, we can actually do this without too much of a problem. Hope all of you can see the vehicle movements. And you can see that you can see that the vehicles are actually lagged slightly, and that is deliberate also. This is all calculated in terms of how these two vehicles need to be lagged, so that that's taking advantage of the width of the lanes. You know, you go past one vehicle and you come to the next vehicle, and that vehicle need to be lagged slightly in terms of their release time. So it's in a way it's a straightforward idea, but it's also I guess a drastically different way of driving, and it would probably scare us. So I'll stop sharing and restart, or I'll share the presentation back again. Okay, moving on. My God, we are all dead if we have this kind of conflicts. But as you could see that if we have technology assistant, and you don't need autonomous vehicle technology or anything for this, you just simply need a vehicle to infrastructure, simple technology of having a device at the intersection, a much cheaper device than having the signal masts and having signals and all that, which is extremely expensive. Instead, you can just have a device that transmits the distances of the vehicles. And you could even have a display within the car that actually shows the cross-direction vehicles coming. And in a level 3, level 4 type of automation situation, the driver could actually have the cooperative cruise control taking over when a vehicle arrives near an intersection. The pedal control will go away from the human to the machine, which is again not a problem. This is fully established, fully verified technology that is available for this. So this is not a problem either. So now what you have to see is how much of accident probability is there. We studied this, so this was a TRB paper that we published. What all we did was to just look at the geometry of vehicles as they move on, and placed around the vehicles a little safety space, 10 feet type of safety space around the vehicle. So we don't want another vehicle overlapping over another crossing vehicle space. So there is the probability for accidents is simply the overlap volume of these tubes. We call it a tube model, a paper that we presented this January at a Transportation Research Board meeting that Peng Yuan had presented, which was on this idea of vehicle tubes. So if you think about a time-space diagram, all of you know the x and time, I mean the distance and time directions. But instead, if we actually make the distance direction an xy space and the time a vertical space, if we do that, then we actually get instead of time-space trajectories, which are curves on a paper, in 3D, these are basically tubes. That tube is basically your vehicle plus a safety zone around it. And if the zones overlap during the simulation, that actually indicates that, okay, that is showing probability for an accident in a stochastic simulation environment. So this has been studied. So this was a paper that we had this year. And so we also established an interesting result that turns out that there is so much of overlap that will happen in car following with rear end collision possibilities, and that we are not doing that. I mean, human beings are able to handle that. Why can't we handle the crossing conflict, which is only existing at one point, not constantly as you are driving? It's just one vehicle, one decision. Should I slow down and wait for that car to go before I go? That decision, this is the kind of decision that we actually make in driving, and that is our our studies. This is just for fun, but our first thinking would be, okay, are we advanced enough to do this? Yes. So I just picked, since my student is from China, I picked an intersection from China, and I picked an intersection that many of you would have seen in Kerala, the Kottarakara junction, which is a historically problematic junction. And I think this picture was taken during COVID. There is no way there are that few vehicles at the Kottarakara junction. But the point is, and Beijing is not that bad. Okay, I'm just showing it for fun. But I don't know how those cars go through. That's from. So my point is that we are technology savvy. All of Asia is, and we are ready to do it. I think we should do this, and we should field test these kind of ideas, which has relevance. Now I'm going to run through a few slides just to show that there is some analysis behind this. But as I said at first, my interest was not to get into all the equations of it. But these are the vehicle tube model that I was talking about, the time-space cases of merging and diverging and car following type of movements. And you can actually study when two of these trajectories in space overlap with their safety region. The overlap volumes can be used as a surrogate for accident probability. So that's where, as can be seen from the simulated trajectories, car following actually involves more human decisions and more opportunities for something to go wrong than crossing conflict at intersections. And especially if you have technology assistance, there is just no reason why we shouldn't try it. Minor adjustments while getting into the conflict zone are enough to avoid collisions. I'm talking about basically tapping the brake just to let a vehicle go through. This is, we routinely do this in Kerala driving, at least. Collision warning systems exist. Onboard devices that show crossing vehicles. If you can imagine a little display that shows the graph, or the network, and just shows in circles or dots that's moving across. You can actually see a car coming because there may not be side distance to see if there is a gap that exists. It's a no-brainer for autonomous vehicles, of course. Okay. So let's go for link-based control. Is the intersection signal must go away? We need freedom. That's what I'm thinking. Then there is this ordered movement case, and I'll skip this, but know that you actually saw this in the simulation video that you just saw. You need to order these and order lane by lane. You should lag the signal timings appropriately for this to work. And it's again straightforward. There is not much of a problem. You can actually develop a matrix-based optimization scheme for it. So simulations have established feasibility. This is just showing some of Pangyan's slides, since he is also attending. A lot of nice work that has been done on the movement vectors, optimization constraints. We studied this sort of a single intersection case. We also studied a case of a sequence of intersections. Here you can actually see some results that are actually significant. You can actually see the average flow rate in terms of vehicles. You can see that this is going up to 3,000 in this particular case. That is 3,000 critical per lane volume through an intersection. Once the density goes very, very high, you can't do this, okay, which we know, which is the case with our existing intersections too. We go into oversaturation. So here, the flow rate will drop, and notice that even at 80 vehicles per kilometer, which is very high volume, this is still giving the throughput that we currently get as maximum, which is something around 1,500 or 1,600. Okay, so this works. There's this question about pedestrians. Now this becomes very, very interesting. We have developed a scheme for pedestrians. Now you will actually need to give some pedestrian signals where every so many minutes you could actually let the pedestrians cross. But the interesting thing is, along a corridor, if you have actually coordinated these flashing greens along the way, then the pedestrian walking along the corridor also can be coordinated with it. So that's an interesting problem, but let's skip that idea also. So that actually is throwing at you something that we are currently working on. As I said, the safety part of this has been studied in a TRB paper that we published. The whole idea and the initial results from those simulations that we are showing, I deliberately didn't show it here because that's part of a paper under review for the TRG conference in December, where I will actually show some of the numbers from the latest simulations on it, and which are actually much better than what I was showing. So that's what I have. I'm just throwing this idea at all of you, and you are the first ones to hear it from Peng-Yuan and I. So please think about it. Maybe at some point we could try a technology demo in Thiruvananthapuram. Trying to do Thiruvananthapuram. So thank you, Dhanyawad, Sheshe, Nandi.
Nandi sir. We'll wait for some questions.
Please.
Yeah.
I hope I didn't take up too much of your time and didn't bore everybody to death.
No, not at all. Those who want to ask question, Tom, you would like to start?
Yeah, sure. Okay, thank you. Yeah, it's a very interesting idea. And of course, we have concerns about user acceptance and translations, etc. Nevertheless, I'm just curious to know where exactly is the control lies. Especially when changing the traffic density or traffic conditions. So this control scheme has to change. So where is that control?
Yeah,
lies?
that control can come in simply from the headway or the flashing green times that we give on the links. That's why it's a link-based control, right? So each of those link signals, if they were going at 1.1 every 1.8 seconds, and we decide that this is not optimal now, we need to go to 2.4 seconds, which will probably reduce our throughput, but maybe that is needed. For safety reasons or whatever reasons, right? Or in terms of the demand reasons, what could ultimately happen is that we might find that there isn't much of a reason to reduce to increase the frequency of the green flashes, but the queuing will actually happen on the links.
So
it will happen on the links, but it will be distributed in the network as opposed to just having it at the key intersections. Because if the coordination and optimization is done properly, then we are actually distributing the queuing to various flashing lights. But in the normal cases, that is, if we have not reached the sort of the maximum flow or maximum throughput conditions, you will typically not find queuing at any of those signals. because they are flashing. And one flash, maybe a vehicle had just slowed down and stopped for half a second, and then it is released. And just like what you will see on a freeway entry ramp. I mean, you may sometimes not see a queue at all there. It just flashes and lets the vehicle through. And then the next vehicle might come in. Now, if you have, if you can imagine maybe a bunch of shops on the side that releases vehicles onto that link, then they will actually first queue at one of these flashing lights, and then they'll be again released. As far as the next link is concerned, you don't have that collective density formation, which will reduce the speed. That is the real problem, right? I mean, our demand, we send them into our network, to our intersections, without controlling them. And so collectively, they increase our densities. They all stop at these intersections where there is crossing. And then you have a problem. Here, that does not happen. Vehicles are gap controlled. So it's basically a link level gap control of vehicles with flashing signals. So the vehicles will come to intersections at appropriate times. There may be some variance. If supposed to come at every 2.8 seconds, maybe one vehicle to the next vehicle, maybe that vehicle speeds up a little. So it comes at 2.2 seconds instead of 2.6 seconds. Not a big deal. A 0.2 second or 0.1 second adjustment can be done by the technology out there at the intersection. So this is basically traffic smoothing and gap control all around on the network links, so that vehicles will come to the intersections at the right times, and they will cross through gaps, so the intersection gets twice the throughput. Does that sort of make sense, Tom, what I'm saying?
Yeah, it makes sense actually. Now, my concern in that case, no, there would be, like for let's say 4-arm junctions, all the four, wherever that flashing light is there should be appropriate, the sensors to understand what is the volume on the other, other approaches also. No, then only
the volume the volume on the other approach, it could be a maximum of some value, and we would actually design it based on the maximum. Now you're bringing up an interesting point, that if you don't have cross direction traffic, you could actually release these vehicles maybe slightly better. But again, remember, we are releasing vehicles in the normal case every 2 seconds from each of these greens. We can't do any better than that, because human drivers cannot follow each other, right, any closer than 2 seconds, right, in car following. So car following itself starts becoming the throughput determinant. So if there is no flow in the cross direction, we don't do anything. We just we just leave these cars to go at this flow. If there is saturation type of flow in the cross direction, then the timing works. Again, it's just that the direction that needs to go through, they get free green. When you're moving through gaps, you're basically getting 100% green at the intersection. It's just kind of weird, right? When you think about it, you are getting 100% green, because every 1.8 seconds you are sending a vehicle through. You can't do any better than that, because car following wouldn't allow two vehicles going closer than once every 1.8 seconds. So per lane, that is the flow that we can get. We can't do any better than that without autonomous vehicle control. Yeah, it's possible if the braking system and everything is improved, we could reduce that 1.8 to 1.3 or 1 point something. If we can do that, we will reduce the timing of these flashing signals even further. But as far as I imagine, this would just simply eliminate most of the queues, so the delays can drastically come down, and throughput, it may not go more than twice or something, or maybe 50% or 75%, or many of the simulations that Pangyan has right now done, we are seeing benefits between 70% to all the way up to 120, meaning slightly more than 2 times the throughput you're able to get without too much problem. And this is simulations involving some variance in the human driving. Some of the simulations were actually done with the transmodeler standard car following relation. So we just show these flashing lights, and then the rest of the movement is like a regular human being, not sticking to anything that we are saying. They're just released, and then they go to the intersection, and then we see how much of accident probability there is. And it turns out that we can get throughput up to 2 times without too much problem in terms of even safety. Of course, field tests would need to be done. But delay, on the other hand, delay is probably going all the way down to 1/4 of the delays that we currently have. Now, imagine that if our intersection delays go down to 1/4, our travel times in many of the networks could end up really going down to half or 1/3. If that happens, then our demand is getting in and getting out of the network that much faster, which means our densities will not go up to the higher levels that we worry about. So it is a circular helping, win-win-win kind of a situation.
Okay, thank you. There are some others also have some questions. So, okay, thank
Please.
you.
Can I see the question? Am I looking at the chat?
No, we'll read, sir.
If you can read, please. Maybe I'll stop sharing. Oh, I'm seeing a question from Anish. Can you hear me?
Yes.
Okay. Yeah, I can read this. So thank you. Okay, it sure works for an ideal case and access control roads, but wondering how different it would be for heterogeneous mixed traffic conditions. Great question. The simulations were showing straight moving vehicles. What about U-turns? You're absolutely right, Anish. All of these questions need to be answered. Not just this. There are a ton of questions. Pedestrians, I already kind of mentioned that would be one of the first things that would come to mind. What do you do about U-turns? Should we allow U-turns, or do we need to design our roads themselves, somewhat differently? I don't have answers on a lot of those. In fact, what I would do if we were to implement something like this is to keep the signals as is and just try this. Just simply with the existing signal control, I would try some gating. Even that would, I think, would really help, at least during the green times that we are showing. Vehicles will be coming at a gap, and this actually causes the gap formation in the streams that are happening on the road, which by itself will reduce half of the queue delays that we end up getting. Just again, remember the area of the queue. If you remember the triangle, right? There is a quadratic increase in the total delay that happens, and that usually happens because vehicles are bunching together. So there will be benefit from this just from doing a implementation and a test of whether people can follow the advice, or whether we can develop a in-vehicle display that brings people at the right time. I would think that U-turns would become almost impossible to. You would have to find a way to go around a block. If it's a city block area, you can. But Kerala networks, if you can't make a U-turn, you're in big trouble in many places. So that's why I was saying that some design changes would be needed. We might just introduce some U-turn lanes in some places. Again, in mid-intersection, you can do that, though. Not a problem. At the gating locations, you can simply allow a U-turn, which like we do at the intersections where we allow a U-turn before the intersection, right? That can be done even in this case, but not right at the intersection. It won't be possible. But yes, a lot of these things have to be studied. That's why I was just saying, this is like a new way of thinking about doing traffic control. Imagining that, okay, we will have technology. We should be able to do this pretty soon, much before autonomous vehicles are driving by themselves. We can have technology-assisted human driving in this form. So I think we have to get there. There is so much to gain from it. We should be able to drastically cut down travel times, save so much of productivity. I made some calculations at national level productivities. Korea was sort of like an example that I used in looking at how much money is lost from long signal cycles. These are back of the envelope calculations using how many intersections are there and how badly timed these intersections are. And I was getting numbers of the kind of 2% of national GDP. 2 to 3% of national GDP. That is the level of loss that we are talking about in productivity. A few percentage of national productivity. That's what we are losing. So that's a lot of money, and we need to start coming up with some solutions. I think that's all I have.
Yes. Any other questions?
Any other questions from participants? We can even mail if we have any comments.
Or you can ask now. You can.
Oh, any of you, all of you can email me. Not a problem. Just send me an email. Like I said, it's a new idea, and wanted all of you to hear it first. The idea itself, I don't know if it is 100% new. There may be people who may have thought about it. We haven't seen anything that actually sort of formalized the design of it. So glad that I'm telling all of you. So any comments you have, criticisms, thoughts, feel free to email me, or next time when I come to Trivandrum, maybe I can come down and have a chat with any of you if you have any thoughts.
That's great. That's great.
I have a quick comment. Can I ask?
Yes,
Yeah,
please.
sure.
Bhargava from ID Madras.
Bhargava.
Hi, Bhargava. How are you?
Good, sir. How are you?
I'm all right. I'm all right.
Yeah,
Good to
very
see
nice
you.
presentation. Professor, can I go ahead, or? is
Yes,
there
Yeah,
somebody
yeah,
else?
yeah. Sure, Bhargava. Yeah.
Okay, great. So I think Dr. Jayakrishnan, I think it's an excellent idea. I really like the idea. I was just wondering, I had a couple of comments. I was thinking, first thing was just looking at a simple case of one lane in each direction. Let's say an intersection with 4 approaches, 1 lane in each direction. That's the simplest case you can think of. And there we're looking at a margin of error of 2 seconds, right, for vehicles to
Yes,
cross.
actually, the example that I ran over very quickly was, I think, that the single lane for 4-way intersection. And our plan was basically like this: if you can imagine clockwise in a north, east, west, south, One flash will happen at time 0, one will happen at time 0.5, one will happen at 1, one will happen at 1.5, back to 2. So going over the 4 approaches, the 4 signals will go off on every 0.5, 0.5, 0.5 seconds.
Yeah,
So
yeah.
north will go, west will go, south will go, east will go. So that's sort of the order. I mean, I may be doing the US order, Indian order may be counterclockwise, something like that. Yes.
Sure, sure. And if you have 2 one-way streets, simplest case of 2 one-way streets, right? So the margin of error is about 2 seconds because he has to cross the intersection within the 2 seconds before the next vehicle comes, right? I mean, there is some.
No, not 2. Actually, we are talking about 1 second. If it is 2 seconds, then the calculations will show that you cannot get a whole lot more throughput improvement. We are talking 1 second.
Okay.
So
But
one vehicle would have gone, the next one comes within 1 second and as low as 0.5 seconds. But 0.5 seconds, a vehicle moves in a 0.5 second, probably 20-30 feet. So thinking of a crossing vehicle going and another vehicle going through 0.5 second later, these 2 vehicles are like 30 feet apart. So it's not that close or anything, is what I'm saying.
Yeah, but when we look at
20 feet apart, I mean, not 30, probably 15, 20 feet apart. So it's not like they're just going to hit. So if you have a collision warning system that will just kind of put a brake, that's all you need. Because all the avoidance you might need would be just a slight slowing down to make sure that you keep at that 5 feet distance from the car that just went past. Does that sort of give you an idea what I'm talking about?
Yes. Yeah. My question is more about, is it possible with human-driven drivers? Because we need some kind of automation to help you navigate within that 1 second PET, right? Post-encroachment time will be less than a second.
No, I agree, Bhargav. I think it is. It may be possible if we actually train drivers. I think human beings can do this, but I wouldn't trust at this point, right? Because it is they may or may not learn. We don't know. I mean, if you look at how many things we do learn when we learn driving, a lot of those things might sound very, very dangerous. I mean, in 1920s, if people were told, "Hey, you have to press a clutch and a brake, and then you need to hit an accelerator, and you have to take a foot off and then press the brake," people those days were scared. I mean, there is historical accounts of this. People thought that most people couldn't drive. In fact, even 15, 20 years ago, seeing a woman drive was such a rarity that people would, how is a woman able to drive? It was like driving was such a difficult thing. Only very few people knew. Remember those days, even 30 years ago. But I think it can be learned. But I'm gonna agree with you that I can't say that that people will learn to drive safely with this. But I do know that the technology to assist it is just not a big deal at all. I mean, you don't need the autonomous vehicles sensor system for this. I mean, you don't need all of the connectivity of the autonomous vehicles, and you only need the collision avoidance technology. You don't need the artificial intelligence and all of that. None of that is needed. So you don't need a thinking vehicle. You just need a vehicle that just follows an algorithm. And the algorithm is very straightforward to avoid collisions in this. That's what I'm saying. So it'll be a cheap technology to put in place.
Okay, great. Thank you very much, Professor.
We can think. We can think. Yeah, thank you.
Yeah, sure. Thank you. Thank you, Professor Matthew.
Yeah. So good, Bhargava. You also joined.
Yeah, good question. I mean, both of you are asking and Anish, I like the question, and I need to hear questions because we both, Pangi and I, are constantly just kind of thinking about all various sides of this. So we'll see where it goes. Maybe later we'll find that we're making some big mistake, and maybe all of you will point that out. We'll see. We'll see.
Over to Shalini.
That was actually a fascinating technical talk. Now I would like to invite Srimati Shalini PN, Senior Scientist, TPED, to deliver the vote of thanks.
Good morning, everyone. It has been such an honor to be part of this wonderful event today. An enlightening and informative talk on traffic signal future by Professor Jayakrishnan, Professor of Civil and Environmental Engineering at the University of California at Irvine. This talk has been very enriching and educative and has detailed about the prospective new technologies that can help us in designing a better signal control for conflicting streams, thereby enabling a safe traffic flow. On behalf of KSCSTE-NATPAC and the entire transportation fraternity who joined us online, I would like to express our sincere gratitude to the esteemed speaker today, Professor Jayakrishnan, Professor of Civil and Environmental Engineering at the University of California. Also, I would like to express our gratitude to all the eminent professors who have joined us online, Professor Tom B. Matthew, Professor CSRK Prasad, Professor Bhargava, and other eminent professors, and all the honorable delegates who have joined us today and blessed us with their presence in making this a successful event. We are also very much thankful to Director NATPAC for his constant guidance and support in shaping this enriching event. Thanking you all once again and concluding my words. Thank you.
Thank you, Jayakrishnan.
Thanks for inviting, and such a big crowd, and so many of you coming. It was inspiring to see all of you professors from everywhere. I would have probably been more careful and may have thrown a lot more details in it if I knew that you will all be there. But hope I didn't disappoint you. Thank you.
Thank you. Thank you. When will be your next Kerala visit?
Probably in a few months. I keep coming, so I'll be there probably in December or so. Actually, I'll be there at the end of August. I'm sorry, I'll be there at the end of August.
Okay.
Thank
Thank
you.
you, sir.
So,
Thank
we'll
you.
sign off.
Good night.
Yeah.
Thank you.
Please.
Good night.
Thank you.
Good night.
Good night. Good night.